Hello students. So up until last class we looked into change of variables in an integral and also change of order of integration, where we can reduce a very complicated integral to a rather simpler form by using either change of variables or change of order of integration. Sometimes it is useful, sometimes it is not. So most of the time we have to judge from our intuition that whether changing the order of integration or changing the order of variable would be helpful or not. Sometimes it also looks like the integral is quite complicated and there is no way we can be able to integrate using the traditional method of integration. Then in that case changing the order of integration or changing the variable of the integration would be the only way out there. So we also worked out few examples in the previous class, and today we will start with something called triple integral. So we know that so this is according to your syllabus. So if we look into your syllabus, then today we are going to cover the triple integral. So today we will be covering basically the triple integral. So today we will be basically covering the triple integral, and so let's go back to the topic. So we will start with triple integral. All right. So now, like in case of function of one variable, let's say f(x), which is defined on an interval a to b, then in that case we can be able to talk about integral of this type. Or if we want to integrate along a curve, then we can also do that here. Now if we have a function, let's say, of two variables, so this was the first type of integral we saw. Now we have the second type of integral, which is basically if we have a function of two variables, say x and y, on a rectangle, let's say a to b cross c to d. This can also be a region. So it can happen that instead of rectangle we have a region. However, the concept would work similarly. So the integral can be defined as integration from a to b and integration from c to d f(x(y) dx dy. Now how do we do the integration? That is something we have already seen. Now suppose we know that we also have three-dimensional geometries and three-dimensional figures, and in such cases we can also talk about triple integral. So triple integral deals with the surfaces which are in 3D. So here in this case we have the range or the domain of integration are basically two-dimensional geometries. So instead of this rectangle we can also have a region which is in 2D setting, but instead of 2D setting we can also have a 3D setting. So suppose if we have a function f(x(y)z) defined on a rectangular parallelepiped a to b, c to d and e to f. So that means now we have a rectangular parallelepiped. Here in this case also we can talk about a triple integral. So we write it in this fashion: f(x(y) z dx dy dz. So triple integral comes from the fact that we have used three integral symbols. So hence the triple integral. Sometimes people also prefer to call it as volume integral, which is also fine. And this dx dy dz is basically the volume element. So this dx dy and dz are the volume element. And here of course how we evaluate the triple integral we will see in a minute. Now we know that in case of function of one variable we could be able to define that upper integral sum, lower integral sum. From there we defined the upper integral and lower integral accordingly, and if the upper integral and the lower integral are same, then we can say that the function is integrable or Riemann integrable. In case of function of two variable, we saw that similar concept works. So, in case of function of two variable, we can also be able to calculate the upper integral sum and lower integral sum, and from there we can calculate upper integral and lower integral, and if they are same, then the function is said to be integrable on that rectangular region R. Now, in case of function of three variable, the concept still holds, and it goes in the following way. So, the definition, we will start basically with the definition. So, integration of a bounded function, on a rectangular let us say parallelepiped. So, it is given by r equals to a to b, c to d, and e to f. By the way, this f here and the function f, they are two different things. So, this f here is basically a real number, and that f denotes the function of x, y, z. All right. And suppose we consider, so let us consider the three partition. Let us consider the three partitions, say P0, P1 and P2, such that we have P0 equals to x0 equals to a less than x1 less than x2 dot dot up to less than xn minus 1 less than xn equals to b. Similarly, we can write P1 equals to y0 equals to c less than y1 less than y2 dot dot up to less than yn minus 1 yn equals to d. And similarly, P2 equals to let us say z0 equals to e, where this one less than z1 less than z2 dot dot up to less than z minus 1, then zn equals to f. Now, these three partitions give rise to a new partition, a partition, say say P of the rectangular parallelepiped which divides rectangular parallelepiped, so PED, PED R, which divides R into so by the way, we can have this one as xn, otherwise it will be a square. So, we take it as a rectangular parallelepiped. So, xn, ym and zp into m and p sub rectangular parallelepipeds. So, parallelepiped. So, it will divide the whole rectangular parallelepiped into mn times p sub rectangle parallelepiped, and where subrectangular parallelepiped xr minus 1 to xr times ys minus 1 to ys times zt minus 1 to zt, where r running from 1 to 3 up to n, s running from 1 to 3 up to m, and t running from 1 to 3 up to p. So, this is the number of how to say rectangular parallelepipeds by which for this interval, this partition P divide actually. Now, we write let WRST equals to XR minus XR minus 1, YS minus YS minus 1, and ZT minus ZT minus 1, all right, which is the volume of this rectangle parallelepiped, this one. So, that is the volume of this rectangular parallelepiped, this here. So, it is basically length into breadth into height. So, length into breadth into height, and now we write let capital M R S T and small m R S T be the upper and lower bound of the function f on this subrectangle, let us say on the subrectangular parallelepiped, on the subrectangular parallelepiped. Sometimes this spelling might be wrong, so don't worry about it. You can parallelepiped. So you can correct that. So this spelling is not an issue. All right. So now that we have the upper bound, we have defined, we have denoted the upper bound and lower bound. I can be able to write my upper integral sum, which is UPF, which is basically sum of all the upper bounds. Or I can write instead of writing this notation. So, I was going to write the whole thing together, but let us write it separately. S running from 1 to m and T running from 1 to P, capital M R S T times W R S T. So, this is my upper integral sum. So, this is upper integral sum, and I can write LPF equals to sum R running from 1 to n, S running from 1 to m, and T running from 1 to P, small m R S T times W R S T is basically lower integral sum. All right. So, this is how we define the upper integral sum and lower integral sum. Now, as for the function of one variable or function of two variable, the infimum of this set. So, infimum of all such upper integral sum for all the partitions for that is basically called as the upper integral sum, and lower integral sum. So, basically the upper integral sum on this rectangle, let us say R, rectangular parallelepiped, let us say R, f x y z dx dy dz is basically the infimum of set of all sums. So, UPF infimum of all such UPF, where for all partitions P is called as the upper integral sum, and similarly the lower integral sum, let us write a lower sign at the bottom, f x y z dx dy dz equals to supremum over all partitions LPF. So, this is basically LPF, and this is called as lower integral. Now, from our classical theory, we know that the upper integral, if the upper integral and the lower integral, let us write here. So, this R means rectangular parallelepiped, all right. So, f x y z dx dy dz, if they are equal, then this actually implies that the function f is triple integrable over the rectangular parallelepiped, and the common value is basically denoted by rectangular integral over the rectangular parallelepiped f x y z dx dy dz is called the triple integral. Is called the triple integral of f on the rectangular parallelepiped R. So, this is how we basically define in general the triple integral of a function f on a rectangular parallelepiped R, like we did for the function on a rectangular domain in R2 actually. Similarly, instead of having a rectangular parallelepiped, we can have a region. So, we can have triple integral. So, calculation of triple integral on a rectangular on a region actually. So, we can have something like calculation of triple integral on a bounded domain. So, like bounded region, here we have bounded domain E. So, the definition goes like this: if f is a continuous function on a domain E bounded by the surfaces z equals to phi x y and z equals to psi x y, then y equals to g x, y equals to h x, and x equals to a and x equals to b. Then our triple integral over the region E f x y z dx dy dz will basically be integral x running from a to b, y running from g x to h x, and z running from psi x y to phi x y dx f x y z dx dy dz. So, that is how basically we will calculate the triple integral over a bounded region. So, first of all we need to identify by what curve the region E is formed actually. So, that can be calculated or sometimes it is also given. So, we can be able to find out the bounded region, and then the triple integral over that bounded region can be given in this fashion. So, we can see that from this form. Which is that first we are integrating with respect to z. So, we are substituting for z, and then we will get a function of x and y only. So, then we will integrate with respect to y to get the function of x only, and then we integrate with respect to x. So, that is the kind of flow chart we are following here. All right. So, these are the two basic definitions in a way for us to calculate the triple integral. So, either the given domain can be a rectangular domain or it can be a region, and if it is a region, then we have to find out these curves actually. So, these curves here, and then this is how we calculate the triple integral. So, now that we have the definition, we will try to work out few examples. So, let us start with our first example. So, the first example is evaluate or express, let us say, evaluate or express, better we use the word express, I equals to integral over the region, let us say R, f x y z dx dy dz over the sphere x square plus y square plus z square equals to a square as a triple integral, as a triple or repeated integral. So, how can we express this integral as a triple integral? So, first of all, the given region is a sphere. So, obviously, and a is a finite positive number. So, obviously, it is a bounded domain. So, I do not know if we can be able to draw the 3D figures correctly, but let us try to do that anyways. So, this is basically our sphere x 0 z and y. So, this is the radius a, and of course, it is a bounded region. So, we have to first find out the limit for x. So, here x is varying from minus a to plus a. So, here x varies from minus a to plus a. Now, what about z? So, z is basically, so if we see the z, the sphere and the z axis going through the center of it, then in that case z is basically varying from a square minus x square minus y square square root to plus square root a square minus x square minus y square. So, z is varying from this point. So, this point to this point. So, that means this point to this point. That means it's slightly difficult to figure out the 3D geometry, but it's varying from minus of a square root of a square minus x square. So, minus of a square minus x square to square root of a square minus x square minus y square, and y is varying from square root of, if we take z equals to 0, then in two dimensional geometry it's basically a circle, x square plus y square equals to a square, where y is varying from minus of a square minus x square square root to a square minus x square positive basically. So, this is our required how to say range for the variable x, y and z, and now we can write that integral. So, now we can write that integral I equals to integral over the region R f x y z equals to integral over the region R, which is basically so here we will have dx dy dz, and this one will be x running from minus a to plus a, y is running from minus of a square minus x square to square root of a square minus x square, and then z is running from minus of a square minus x square minus y square to square root of a square minus x square minus y square f x y z dx dy dz. So, this is the required form for this integral in terms of how to say triple integral, where now we have the limit of the integration. Of course, if we are given a function, then this will give us the volume bounded by this region E for that function f. So, basically if we have the function f, then we can be able to calculate this volume integral quite easily. So, now that we have seen the first example, let us go to our second example. So, here it says evaluate x plus y plus z plus 1 whole square dx dy dz, where the region is x is greater or equal to 0, y is greater or equal to 0, z is greater or equal to 0, x plus y plus z less or equal to 1. So, this one. Now, here we have basically a region. So, here we have basically a region which is x plus y plus z is less or equal to 1. So, we can draw it something like this. Now, we have to consider the fact that x is positive. So, that means all the points of the region which are lying on the positive side of the x axis. Similarly, y is positive. So, we have to consider all the points which is lying on the positive side of the y axis, and then we have to consider the point z greater or equal to 0. That means all the points which are lying on the positive side of z axis, and then x plus y plus z equals to is less or equal to 1 is the upper part of the plane that is how to say, forming a bounded region basically. So, here z varies from 0 to 1 minus x minus y, y varies from 0 to 1 minus x, and x varies from 0 to 1. So, we have got the limit of the integration, and now we can calculate the integral. So, basically triple integral x running from 0 to 1, y running from let us write these integrals a bit apart, so that we can write these things neatly. Y running from 0 to 1 minus x, and z running from 0 to 1 minus x minus y. F x y z is basically our x plus y plus z plus 1 whole square dx dy dz, and now what we will do is now we will integrate this integrand here. So, this will require some time to perform this integral. So, we are running out of time in this lecture. So, we will continue with a similar example in our next lecture, where we will evaluate this integral, and we can calculate this triple integral. So, I thank you for your time today, and I will see you in the next class. Thank you.